So hello, today we will continue with chapter 7 and, finish chapter 7 because it's Wednesday. That's what we do on Wednesdays, finish chapters. Don't forget homework for chapter 6 is due tonight. Yeah, where we left off was I was talking about refraction, that when light hits a transparent material, when it first hits it, it bends. And I had actually ended with giving some index of refractions. Interesting thing, when people talk about mirages, or you look at the road and it looks shiny like it's wet up high, that's what a mirage is. It looks like the things are wet when they're not. What that is actually refraction. What's happening is that the index of refraction actually can ever so slightly change for something with temperature. And when you look at the road, what you're seeing is light coming from the sun, reflecting off the road and going towards you. As the light travels through the air, when it hits areas of different temperature, air, it'll get kind of bent and it'll look kind of wavery, shimmery, because what you're seeing is the air kind of bending a little bit as the air moves and the hot air rises. Another interesting thing, that's kind of like a side note. I really should have done that last class, but I didn't. So, oh well. Another interesting side point is something called total internal reflection. You see, refraction can only happen for certain degrees, for certain angles. And you can actually solve this mathematically due to the nature of the sign in Snell's law. But the general idea is if you're going from something of a higher index of refraction to a lower index of refraction, an angle will exist called the critical angle. That anytime you come in at a sharper angle than that, the light will not refract, instead will reflect. Once again, hence the name total internal reflection. And then if you shine light out of water into air, you're going to get some angles where the light penetrates and some it doesn't. I can actually show you this with this prism. That when I shine this light on the prism like so, you can see that the light is not leaving the. Let's put this down here. The light is not leaving the right side of this prism. It's just reflecting inside. If I start messing with the angle, well, I guess I can't find it. I didn't mess with it enough. You can see the light though is refracted when it enters. It's refracted again when it leaves. But inside, it's always bouncing off. Just because the angle is so steep that it's coming in at that it cannot refract. This is why we cut gems the way we do. Diamonds are cut with a very set shape. And what the shape does is it makes it so that all the light that hits the front of it refracts into the diamond and then does total eternal reflection and doesn't refract out the backside, but instead reflects. And it reflects across, reflects again, and will come out the top. So all light shined into a diamond, it'll direct it back out at you. What this does is it looks shiny because all of the light from everywhere, it's pushing back towards you. Nothing is going through out the other side because we just cut the angles so sharply. It is also how a fiber optic cable works. A fiber optic cable is just a glass cable. And what happens is because of the length of the cable, that the light can normally refract out of it. But because of its long and thin, that when you go to an angle, we'll have total internal reflection. This GIF to the bottom left kind of shows it. That the light doesn't leave the cable, it stays inside, bouncing down the length. And in fact, here is something. This is a piece of glass to work as my fiber optic. When I shine light on the end, which as soon as I can manage to hit the end, apparently. You think with me video, I would, cut out the useless bits, but I don't remember do that. When I shine light on the end, you can see that the light bounces through it. I'm going to pause this for a second and actually make it bigger again. You can see the light wave kind of bouncing over here, then here. You can see it kind of bouncing through a little bit, and here kind of curving with it a tiny bit because of the material. The light stays inside. because of total internal reflection. It's a way to make light follow a path you want with a negligible loss in intensity. Question so far? Now, I've glossed over something real big here. You see, I've been saying just like, okay, so everything has an index of refraction. You shine light, it's going to bend. How much it's going to bend based off the index of refraction. It's actually a tiny bit more complicated. You see, the index of refraction is not a set value for a given material. Last class, when I gave the index of refractions, and I said these are the values, that's kind of stretching it a little bit. What it really is that the index of refraction ever so slightly changes for different wavelengths. Take, for example, crown glass. That table I just got rid of says the index of refraction in glass is 1.52. But actually, it's 1.51 for red and 1.53 for violet or dark blue. You see, for most materials, the index of refraction for violet is bigger than the index of refraction for red. And so if you shine a single wavelength onto something, like my laser here, I shine one wavelength, it all bounce the same, it's fine. But if you shine multiple wavelengths of light on something, like you take a white light and you put it through refraction, what's going to happen if you take a white light and put it through refraction is that each color will refract a slightly different amount. And for me, stupid. For like big angles, you probably just see, okay, it's mostly white light. But even on this big angle over here, it's a little more red on this side. It's a little more violet on this side. And in fact, if you get it right, you get, for white light, you get a pretty nice rainbow coming out. What it is just, it's following Snell's law, that the light hitting this is refracting. And it's refracting based off that n1 sine theta 1 equals n2 sine theta 2. It's just the value of n is slightly different for each color. And since the value of n is slightly different, theta is slightly different. And you can go and get the individual colors. This idea is called dispersion. And that anytime you refract light through a medium, you always have some dispersion. It is not always noticeable. You know, back here when I had this bigger angle, like here, most of this light was still look kind of white. It wasn't dispersed that heavily. But if you hit it just right, it can become very, very obvious. And there's a way to separate light into its various wavelengths using a prism. Now, why the index of refraction changes with wavelength? We already said that the index of refraction is the speed of light in a vacuum over the speed of light in a material. And we also know that the velocity of any wave is wavelength times frequency. And so for electromagnetic wave, the speed of light is wavelength times frequency. But if you're in a material, your speed should be that speed of m. Now keep in mind that when something hits a material, its wavelength changes. But what we view as color, that's really frequency is what causes color. And therefore, this equation here for C of m, I can plug that in for C of m in the top equation. And the general idea is the smaller the wavelength is, the larger n is. Sorry, wavelength is what changes color. They both change, but wavelength is how we define it. And so that as the wavelength starts changing, it changes n. That anytime light goes through a prism, anytime light is refracted, it'll slightly shift and separate the wavelengths. Now, the reason we see it so well with a prism, like I see it real well here when the light leaves the other side of this prism. I don't see much of it when it enters the prism, but theoretically there should be this dispersion when it enters the prism and when it leaves it. I can see my light bends. If you look at this very closely, you can see that the light is going this way, and now is oops. Let's do it like this. At the bottom of this light is going flat here, and here is coming up at an angle, and here is going at a crazier angle. but we don't see the dispersion there. The reason you see it in a prism is because prism involves light refracting twice. Light refracts when it hits the prism and enters it, and then it refracts again when it leaves the prism. What is we define delta as the total change in angle. That if I wanted to solve delta for this guy, I would say here the light is going this way, and when it leaves the prism, the light is going, yeah, that was a really bad line. That's better. The light is going that way. So I'd say delta is this total angle here. What happens is when it gets refracted, as I said, it'll split twice. It'll split when it enters the material, it'll split again when it leaves the material. And this will cause us to really accentuate the separation of light and see the different colors much better. Any questions?
No.
Fun fact, this is also why sunsets look the colors they do. When the sun is setting, you can actually see the sun after it goes under the horizon. What it is that once again, air's index of refraction isn't 1. Air's index of refraction is 1.000, 3 zeros, 2 zeros? 3 zeros. 1.00, let me make sure I get it right. 1.00029. It's really close to 1, but it isn't quite 1. Oh, I had on the next bit. What happens is when we look at the sun, the light from the sun comes and will get refracted when it hits the atmosphere. Very, very, very slightly. But if something travels real long, a little bit will go a long way. And so what will happen is the sun's light gets bent a little bit. When you look at a sunset, the sun, where you see the sun, is actually not what it is. The sun will be a little further below the horizon because the light is bending. But what happens is when this light bends is the light will bend differently depending on the wavelength. And so if the sun is high in the sky, all of the colors from the sun's light will get separated a little bit, but they're all still basically going to hit you. When you're right at a sunset or a sunrise, what's going to happen is that you're just nicking the edge of the sun's rays. And since there's a slight difference in amount of the dispersion, what's going to happen is that you might be at the very, 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 very edge and only catch the very, very, very edge. Really, also to make it a little more complicated, moisture in the air disperses blue. And so most of the time the sky looks blue because the air absorbs the blue light and spreads it out. That's why the sky looks blue. The sky does not disperse red light quite the same. And so since you're at the very, very edge, basically no blue light is hitting you. You see just the reds. Now, sometimes it is useful to cause refraction, to purposely cause refraction. I'm doing it now. Without my glasses, my computer screen is a blur of things. My glasses is what they're doing is they're refracting the light. They are taking the light and bending it to match. Sometimes, ignore what the text has, but sometimes you might have some text and you want it bigger, and you can use a type of lens to try to enlarge the text and make things bigger than what they are. This idea of using lenses to refract light is a way to help us see things. And if you want to purposely refract light, we would normally use lenses. Lenses are just a piece of glass or plastic made with 2 refracting surfaces, one on one side, one on the other. When light hits this lens, and yes, I'm going to look upside down in this lens like this, we'll come back to that idea. What's going to happen is it will refract when it enters the glass and refract again when it leaves the glass, and can direct the light to do various things. Like a curved mirror, we can make things bigger or smaller or make them upside down. As you can see, I become upside down here. Or if I move it around, well, it just didn't really make me bigger at all, it just made it all fuzzy. You can start really messing with the images. a way to direct light. Now, lenses traditionally are in two categories: converging lenses and diverging lenses. Converging lenses are any lenses that are thicker at the middle than they are at the edges. You can't really tell, but this one's a converging lens. A diverging lens is any lens that is thinner at the middle. Now, we're only going to talk about biconcave and biconvex. And sometimes I might just say concave and convex just because easiness. But a biconcave is one that both sides of the lens are concave. Once again, concave means coming in. A biconvex is one where both sides go out, just like a mirror. Now, here's the thing. A concave mirror is a converging mirror. A concave lens is a diverging lens. They're going to be very different. So if I say concave, yes, a concave mirror was the ones that looked like this when you were shining light on the inside. It was like a cave. This was converging. But a concave lens is this guy over here. It's still like a cave, but this would be diverging. We're also only going to look at thin lenses. Thin lenses are ones where the thickness of the lens can be ignored. And just like a mirror, we are going to define, I want to check to make sure I didn't skip a video. Not yet. And just like a mirror, we are going to define something called the principal axis. You see, for a lens, a biconcave or biconvex, what's going to happen is the principal axis will just be a line straight through the center. And just like the mirrors, you will have what is called the focal point. A converging mirror or biconvex will take parallel light and focus it to the focal point. A diverging lens or biconcave will take the light and focus it away from the focal point. See, if I go back to my video lens, here's my parallel light. This is a converging lens. All of the light focuses to right here. That means that is the focal point. Of note, officially, lenses actually have two focal points, and you'll find most diagrams will label it twice, one on one side, one on the other, where if you're doing biconcave, convex, the distance would be the same on each side. That's just because you can look through a lens either way. If I instead put in you can see when I move the lens to the side, the distance to the focal point from the lens didn't change. It just, distance focal point lens didn't change. A diverging lens separates the light. And if you take a diverging lens, and if you follow all of the rays backwards, you'll find it is as if they all came from one point. That would be the focal point also. And so light with a converging lens, the light is focused to a point on the other side. Light with a diverging lens, it's as if it was focused from the other side, assuming the light that's coming is parallel. Any questions though? Now, unlike a mirror, and this is actually not 100% true, this first sentence, so I want to be careful. Unlike a mirror, it's not a simple relationship between the focal length and the radius of curvature. They are related. There's something called the lens maker's equation. It's a very complicated equation, very complicated. And so it is related, despite what that says, but it's not like a direct, like half the radius of curvature, that's the focal point. It's nothing that simple. But like a mirror, if you know the focal point, that'll help you to see what a lens does. That if you look at an object through a lens, it'll change the image of the object. Now, in the mirrors, I said a real image is one you could focus on a screen. And when we looked at mirrors, I said if the object and the image was on the same side as the mirror, that meant it was a real image. And if the image and the object too far. If the image on the object were on the opposite side of the mirror as each other, that was a virtual image. Lenses are opposite. A real image on a lens is one that's on the opposite side of the lens, and a virtual image is one that's on the same side. It's because you look through lenses. And what is a real image is one that can be focused on the screen. So any image that can be focused on a screen is one that goes through a lens. That's basically how a camera lens works. My webcam right up here, it has a lens in it. It's focusing that light. If I go and try to put this other guy in, and you get this me upside down in the video, what it's doing is it's focusing that light. It's inverting me, and we'll come back to that in a second, but it's just focusing that light. Now, converging lenses will sometimes give a real image and sometimes give a virtual image. It depends on how far away you are. If your object is closer to the lens than the focal length, you will get a virtual image. If your object is further away than the focal length, you'll get an inverted image. That's why when I go back to this hue, this IP, you can see when it's really close, I just make this bigger. I gotta make this so the light can shine through here. For this V work. When I start moving it away, you can see I can make this V bigger. But if I start getting far enough away, yeah, it's not gonna focus. I'll do it with this. When I have it real close, you can kind of see me just blurry because it's not very clean. But when I start moving it away, you start getting an image of me upside down and things. But the image will change depending on the distance. In fact, anytime your object distance is less than twice the focal length, the image is magnified. Anytime your object distance is bigger than twice the focal length, the object is reduced. And it might be inverted or upright depending on which one. Now, you don't need to memorize these right here or know them. I'll come back to why that is in a second. But that being said, if you have a diverging lens, a diverging lens will always be an upright, virtual, and reduced. And this is information to know. You could go with this, but honestly, I don't have this shit memorized. Anytime I need to answer something like this, I just solve for it. Just like a mirror, we did mirror diagrams to say exactly what an image looks like, look through a curved mirror. We can do lens diagrams. And the lens diagrams will tell us what exactly the image looks like through the lens. The logic is going to be kind of the same. You see, for a mirror diagram, you do two lines, one straight across through F, and then one through point C. There's no point C on a lens. Your lines are going to go straight across through F. That is still true. But your other line will go through the center of the lens, wherever the middle of the lens is. And just like with a mirror, you'll draw a little arrow wherever they meet, and that is the location of the image. The one trick here is between a converging and a diverging lens. A converging lens focuses light to the focal point on the opposite side. A diverging lens focuses light to the focal point on the same side. If I was doing this mathematically, there'd be some negative signs involved to help push this. When you do this, keep track if it's a converging or diverging lens. And depending on which one, that'll tell you which focal point to go to. Okay. Once again, I don't think this really makes sense till I do it, but any questions here before I start doing it? Make sure I didn't miss a video. Nope. We good? Okay, so let's do one. So here's a lens. I can say, where is the image and what does it look like? I would draw two lines. The first line comes straight across and then goes through F. It'll go to F on the opposite side of the lens because this is a converging lens. I didn't actually say it was a converging lens, but I can look at the picture and see it's bigger on the inside, middle than the edges, make it converging. I'll then draw a second line. The second line will go through the center of the lens. I mean this point right here. That's the center of the lens. Wherever they meet, that is my image. And I can say this image is a real image. It's real because it's on the opposite side. It is inverted. It is inverted because it points down. And as for magnified and reduced, honestly, I think it's the exact same size. I think it's neither magnified nor reduced. which is a third option though. Let's do another one. Where is this image located? Once again, a converging lens. I can tell because it's bigger in the middle. And I draw two lines. One straight across through F, and the other one through the center. Now I can look at these lines and say they're moving further apart. Since they're moving further apart, they're never going to meet. And just like a mirror, if your lines are never going to meet, continue them back the other way. And I'll say, here is my image. My image is virtual. It can never be focused on a screen, is magnified, and is upright. That was the same as what I was doing. What I was doing with this guy. That when it was super close, it made it. I really wish I could get the light to go in here better. It's because the light isn't quite in the same spot. The cameras and the light are in different spots. You know what? Hold on. Plan. Well, light. No, plan failed. It'll and it's a virtual image when I do this. See, it doesn't. You can still see it, but it's virtual because it can't be focused on a screen. But it magnifies when it's super close. Now, officially, I would say this is a negative image distance because it's to the left, but I'm going to be pretty good about how I accept that. If you have a diverging lens instead, the process follows the same. It's just when you go straight across into the focal point on the same side. Anytime you have a diverging lens, go to the other focal point. Your second line is identical. You go through the center of the lens. And this one kind of missed the center. Like they went to this kind of bothers me. Once again, this is stolen from a textbook. I'm too lazy to make these myself. But they went to right there. This really should have gone to right here. I don't know why they missed the center here, but they did. And wherever they meet, that is where my image is. This is a reduced image. It's reduced because it's smaller. This is a upright image. It's upright because it points up. And it's virtual because on this object and image are on the same side as the lens. Questions? Okay. That is ray optics. We're not done today. Don't get me wrong. We still have half the class. But that is ray optics. That is everything you can do with light with rays. And how we can work out what light looks like when it passes through a lens or a mirror, be it curved or flat. And that is just some of the properties of light. See, way back at the beginning of class Monday, I said light can be broken into two categories. Ray optics. Oops. Where's my ray optics? Here we go. Ray optics, also known as geometrical optics, which is just treating light as a ray, and physical optics, which is the actual properties. And so for the rest of today's class, I want to talk about some of the physical optics properties of light. Okay? You see, light is really a wave. Light is electromagnetic waves. What it is electric fields and magnetic fields oscillating perpendicular to each other, kind of like this. But what happens with light as a wave is that the direction, most light, like you just shine light on something, it is called unpolarized. What it is, the electric fields are random. The electric field might be going this way. It might be going this way. It might be at this angle. It can be going in any, what is up and down can be any direction. See, if you were to look at the wave coming straight to you and just say the line is what direction the E field goes between, you can say this symbol to the right is supposed to be doing that. It says it's going anywhere. This like chaos symbol. Sometimes though, you can make it so that all the electric fields line up. If you make all the electric fields line up, that is called polarized light. And I'm going to switch glasses for this and then talk about why in a little bit. In polarized light, and these are polarized glasses, what's happening is it's going from all the electric fields going any which way to the all in a straight line. They all line up perfectly. And what it's doing is it's taking all the light that is not straight up and down, but at any angle, and is going to separate it. It's going to go and make it so that no, it does need to line up. Get my wife's glasses too. And so if I shine this through my sunglasses, when I shine this through my sunglasses, what I get is, yeah, it just makes it darker, but it's also limiting the amount of light that passes, what its polarization is. This is going to go from allowing light that's going in any direction to just up and down. See, these glasses, they use something called selective absorption. What they do is they transmit light that is only polarized in one direction. Traditional sunglasses allow up and down, and they block out anything that's polarized side to side. I'll get why that is in a second. And when I shine light through these polarized glasses, now the light is polarized. That's what this does. It transmits only things where the electric fields are straight up and down. And anything that the electric fields at any other angle, it's like, nah, we're not letting that through. Only light up and down is allowed through. If it's going any other way, we're not taking it. Now, polarizers like this were first discovered by a man named E.H. Land. He called it a polaroid because it polarizes. It's a long chain of hydrocarbons. It's this whole thing with like organic chemistry that I'm not going to get into because organic chemistry is dumb. It is complicated though. But here's kind of the neat thing. When I put this here, it only allows light that is polarized up and down. If I put this one here, it would only allow light through that is polarized up and down. If I put both of them, it's a little darker, but you can still see my face through this. If I move forward a little bit better, right? You can still see my eyes minus the reflection. I'm trying to not get the reflection, but I don't think that's going to happen. There you go. You can still see me. That's because both are only allowing up and down light. But if I put them perpendicular to each other, no light is passing through. You can read the selective absorption writing because that's the reflection, but it's not letting any light through. While when they were parallel, you can still see my face. Here, let me show this better. So here's my two polarizers. If I start turning them relative to each other, it'll go and change how much light passes through. That when they're both in the same direction, basically the equivalent of both these glasses flat, it'll allow basically a good amount of light through. But if I move them 90 degrees relative to each other, it won't allow light to go through. The reason for this is because the first polarizer is only allowing light to go through in a certain way. Once again, sunglasses will be up and down. If I put another one pointing the same way, if one says I only allow up and down, and the next one says I only allow up and down, they're both in agreement they'll allow the same amount of light through. But if you put one that says I only allow up and down, and then you put another one that says I only allow left and right, what's going to happen is nothing will get through. And so polarizers will change how much light goes through depending on the angle between them. Follow something called Malice's law. You can mathematically figure out how much light will go through depending on the angle between them. But the general idea is if the polarizers are parallel, that'll be when the maximum light passes. And if they're at an angle, there will be less light passed. And as you start changing the angle, you can change how much light can pass through the polarization. Modern 3D movies, they use this. 3D movie glasses, one of the lenses is polarized one way, one of the lenses is polarized the other way, and the movie has everything in two polarizations. So one eye only sees the stuff polarized one way, the other eye only sees the stuff polarized the other way. It's better than the old school color-wise. Now, it might lead to the question of why do we polarize our sunglasses? Like, it's cool. My glasses only allow light polarized one direction. Who the fuck cares? The answer is you do. You care a lot. Interesting thing is when light reflects off a surface, anytime light reflects off a surface, it becomes polarized. And what it is, it becomes polarized to have the polarization match the surface. That if you have light shining off a body of water, like this GIF in the upper right, What's happening is when the light bounces off that little pond, it's all becoming linearly polarized. And so what you're seeing is you're seeing a lot of reflection. When they put the sunglasses over the camera, you now can see the tadpoles, I'm guessing, in that water. You don't see reflection. We polarize our sunglasses because it reduces glare, it reduces reflections. This GIF in the bottom right is an advertisement for a polarizing lens for a camera. And what they're showing is without the polarizing lens, the book one I don't like as much. Without the polarizing lens, you see the surface of the water a lot. With the polarizing lens, you can't see it. Without it, you see the reflection of people. With it, you see through the window, and so on. What it's getting at is that because light, when it hits a material, some will refract, some will reflect. And what this would do is remove all the reflected light, because all of the reflected light is linearly polarized. That's why we polarize our sunglasses. Okay? Any questions? Okay. I think I have one more video, but I want to check. Okay. One of the other important things about the wave nature of light is something called diffraction. Let's say someone talks to you from outside a door, right? And here, I'm just going to draw this. Let's say you got a room with a door, and you're standing right here, and someone right here yells into the room. If someone right here yells into the room, a wave is going to pass through, a sound wave is going to come through the doorway. But you're still going to hear it, even if you're around the corner. The reason why is wave does something called diffraction. Anytime wave goes through a slit, it'll spread out and will actually get bigger than the slit it started with, and will make a just spread out. It happens anytime it happens. It's more obvious when the slit is smaller. This bottom picture is water waves going through a slit, and what you can see is that with the big slit, it's mostly still flat with a little bit of curvature, right? Mostly flat, little bit of curvature. But with a small slit, they're like fully rounded. This is a thing that happens when light goes through a slit. All waves do it, light is part of it. That when these waves pass through these slits, we'll get a different shape. Now, as I said, this is only seen when light goes through smaller slits, though it's normally seen. To see diffraction, you need the slit to be smaller than the wavelength of the material. And so diffraction only really happens when, yeah, you have small holes or very long wavelengths. Sound wavelengths are huge, they're like kilometers long. So the sound diffraction will happen anytime the door is closer than, or the hole is smaller than like kilometers. But light does follow diffraction, but light has a very small wavelength. And because light has a very small wavelength, it is uncommon. You need to have a slit that is really, really, really small. Take, for example, my green laser pointer. My green laser pointer has a wavelength of 485. Don't hold me to that number. That might be off. My memory isn't what it once was. But I'm pretty sure it's 485. Of 485 nanometers. It's somewhere between 400 and 600 nanometers. I forget the exact number. That is really tiny. That's 4 times 10 to the negative 7th meters. And so to see the diffraction of this light, we're going to need a slit that is smaller than 4 times 10 to the negative 7 meters. You can be a little bit bigger and see it somewhat. And this does happen though, that if you shine light on something, and especially you shine laser light, where laser light has only one wavelength, on a very small slit, you can see diffraction. See, here's something else about this. There's something called interference. All waves follow what is called the principle of superposition. When two or more traveling waves encounter each other, they can go and interact with each other. If big pieces line up with other big pieces, they can do what is called constructive interference. That if I have these two waves meet, these two blue waves meet, when they meet up, they just look like a much bigger wave for a second because they just constructively add. However, if you have two waves line up that are pointing in opposite directions, that this one is up while the other one is down, or vice versa, you have destructive interference. This happens when waves are out of phase. And so when these two waves meet, what's going to happen is they can cancel each other out for a split second before they pass through each other. That's what destructive interference is. But here's the thing, light does this. When light waves meet, they can have constructive or destructive interference. And this has some kind of interesting effects. Let's say you have oil leaking from your car. How you'll probably know you have oil leaking from your car is you look at the ground and you see some rainbow pattern. Or you got a soap bubble, and as the soap bubble goes through the air, it's nice and shiny and colorful. This is called thin film interference. Anytime you have a very, very, very thin film of a material that light can pass through, what's going to happen is you'll see these rainbow effects. The reason why is because we're looking at the interference of the different wavelengths. That some regions look more red because red there is constructively interfering and blue is destructively interfering. Some places will look more blue. That's because their blue is constructively interfering and red is destructively interfering. See, what's happening is when you have a thin layer of oil on something, is that light is going and reflecting off the oil. But some of the light is refracting through the oil, going and then reflecting off the water instead. That means you have light that traveled straight from the top of the oil to your eye, and some that passed through the oil then to your eye. These lights traveled a different amount of distance. And so with the wave, for the wave here and the wave here, whether the peaks line up in constructive interference or opposite in destructive interference, which just vary with different wavelengths. And so we'll see the various colors based off whether you're adding up or subtracting. This also causes something called the Young's double slit experiment. The Young's double slit experiment helped prove that light is a wave. What the Young's double slit says is that if you take light and you do like one wavelength time, normally done with laser light, and shine it through two very small slits, you'll get a series of dots. Right now, I'm shining green light on two slits that are 0.25 millimeters apart, and each slit is 0.04 millimeters wide. And what happens when I focus? Come on. Seriously, I need to trim my videos. Is that I see a series of bright spots and dark spots, a series of dots. If I start changing the size of the slits, I get a different pattern. Well, what I was going through there, that's why I changed the focus. I did that on purpose here. Is I was going and changing the size of the slits and the space between them from 0.04, from slits being 0.04 to 0.08, and the space between them from 0.25 to 0.5. And so when I start changing the size of the slits or the space between the slits, I'll get different patterns of bright spots and dark spots, depending on those variables. Now you'll notice, or you might not notice, but I'll tell you, is that the first two look pretty identical and the second two look very identical. That's because the slit space has very little effect, the space between the slits. It's just the slit width. But when I changed the slit width, that changed what the dots looked like. And the reason why is that when light goes through these slits, and once again, you have to use a single wavelength, laser light works well for this, is you're getting constructive and destructive interference. That constructive interference will be the bright spots. Destructive interference will be the dark spots. And the reason why is what you're looking at is that what the light is going to travel through the slits to get to a point. And if you go up and down the screen, you will find spots like right in the middle, you have a constructive interference. The distance light traveled from S1 to that point, and the distance light traveled from S2 to that point is the exact same distance. You'll find other spots where they go a multiple number of wavelengths. That if it goes, the distance is if the distance S1 travels, if however much longer it is than the distance S2 travels, is just a multiple value of a wavelength, like it's one wavelength more or two wavelengths more, you'll also get a bright spot with constructive interference. But if they travel at a half wavelength different, you'll get one being up high when the other one's down low. They can have destructive interference, and you'll get dark spots. That will get these dark spots in between each bright spot because that's just where the destructive interference happens. Does this make sense? What's really nuts is this also actually works with single slits. The reason it works with single slits is a little more complicated. I'm not going to get into that in this class. That's a physics 2 topic. But what I have here is 4 single slits. 1.02 millimeters wide, 0.04 millimeters wide, 0.08 millimeters wide, and 0.16 millimeters wide. If I shine light through the slits, I still get these bright and dark patterns. And that when I switch from one of these slits to another, it changes the pattern a little bit. And all it is this constructive and destructive interference, that the constructive and destructive interference of the lights going through them. And it works with one slit, works with two slits. Logically, it should work with a different number of slits. And it actually works for however many slits you have. A diffraction grading, where this is a diffraction grading in my hand, is a way to separate light into its various wavelengths. We talked about these 2 chapters ago. 1 chapter ago. A diffraction grading would take white light and split it to all its wavelengths. And what it's going to do, and I don't think I have a diffraction grading video open on this. I should find one. What it's going to do is separate the light into all its various wavelengths. Now, when I put this here, you can kind of see a rainbow pattern going over my face in the video. Because it's just going to cause constructive and destructive interference through all the thousands and thousands of slits. Okay? Any questions though? Okay. We're going to stop there. That's the end of this chapter. I will start chapter 8 on Monday. Don't forget your homework. Don't forget your labs. Have a good weekend, and I'll talk to you later.